Hey guys, hi future doctors. So we meet again. I'm Dr. Shivangi Shukla, and the last session a couple of days ago we started with enzymes. We finished the structure of enzymes, the mechanism of action of enzymes, and we touched upon the enzyme kinetics. And we discussed about the free energy, the Gibbs free energy, which determines the activation energy threshold. So till that part, we have discussed the kinetics, and now we'll discuss kinetics in detail and also a few topics about enzyme regulation. So both these sessions, the first part and the second part of enzymes, they should be read together whenever we are reading, because all of them are the knowledge that we're acquiring are correlated. And also there's a lot of application, so there will be a lot of to and fro between both these sessions. Okay, so make sure that if you have not attended the earlier session, you go back after this and attend the earlier session, and then you can jot down your notes and always read both these two parts together. Okay, because it gets very heavy to read it in a single sitting. So you just read it, the first reading or the first understanding, we can divide it in two parts, and after that, whenever we are revising, we can complete these two parts in a single go. All right, so today we'll begin the we will be touching upon the earlier topic quite a few times in this. After this session, I will be organizing a small MCQ based session for all of you guys in my next class. So it will be a revision of sorts for this entire unit. Okay, the structure of enzymes and proteins, and the mechanism of action of enzymes, the kinetics, enzyme kinetics, and regulation of activity of enzymes. So after we finish this session, in my next session, at the start or maybe after the end of the next session is going to be on the respiratory chain and oxidative phosphorylation. So that you must be aware of, because you must have read about it in your class 12th while preparing for the entrances. So you must be quite aware of that topic. But in any case, we are going to touch upon that topic also in detail. We'll read that. But in that session, I'm going to put up an MCQ based quiz for all of you guys, maybe 10 or 15 questions, to summarize this entire unit, what we have learned in these past 3-4 sessions. Okay, so go back and revise all of these sessions before you sit for the next session, so that you are very up and about and ready for that MCQ quiz. Okay, so without further ado, let's begin. All right, now we had touched upon this activation energy concept in the last session, had we not? What is activation energy? Now, activation energy is that energy which is required to reach the transient state intermediate. Now, what is the transient state intermediate? Now, suppose there are two substrates. Okay, so one is the entering substrate. Okay, one is the en entering unit. Now it comes and reacts with the leaving unit. Okay, the entering unit will come and react with the leaving unit. The leaving unit is bound to this enzyme here. Okay, this enzyme will come out unscattered, or it will come out unmodified. Now once this entering unit and leaving unit combine, the result is going to be this. Okay, now what, the leaving unit will go. Okay, but before this is formed, this is the product, before this is formed, this is actually occurring in a two-step reaction. All this we have read in the next session, so I'm just revising it. If you're not understanding what the entering unit is or what the leaving unit is, you can go back to the earlier session, the first part of enzymes. So it occurs in two steps. Okay, very fastly occurring, closely occurring two steps. The first step is when the bond between the enzyme and the R group, between the entering unit and the R group, has just started to form, and the bond between the R group and the leaving unit has just started to degrade. This is the intermediate. So this is the intermediate where there is no proper bond between E, R and L. Okay, and the free energy of formation of this intermediate is what is known as Gibbs free energy of formation of the intermediate, delta GF. Now this intermediate is going to break down, and how? There will be a proper bond formed between E and R, and L is going to leave. So this intermediate has now decayed or converted to the product. So this is the Gibbs free energy of decay of the intermediate. All right. Now the energy required, this gives free energy of formation of the intermediate. This energy required is what is the activation energy. That means if this reaction can proceed till this point, then it is going to smoothly proceed further as well. It is like a watershed. It is like a tipping point, like this. If it can proceed till here, it is going to proceed further as well. It is like a watershed or a tipping point. Okay, it is like something is, you have to push it till it just about falls down, and then it is going to fall down on its own. Got it? So it is like a tipping point. After this, the reaction is going to take care of its own. You need to supply it with this much energy to activate the reaction. Okay? So this is what the concept of activation energy is. Now, what is the function of enzyme in a reaction is, every reaction is going to have some kind of an activation energy. The function of an enzyme is that the enzyme lowers the activation energy threshold for a reaction. That means the amount of energy required for a reaction to proceed is lessened by the introduction of an enzyme in the system. Understood? So this is what the function of an enzyme is. This is in general the function of an enzyme. Then this enzyme, how does it do it? It stabilizes the transition state intermediate. This intermediate is stabilized, the formation of this intermediate is stabilized by the presence of an enzyme. And how does the enzyme stabilize it? There are a lot of mechanisms like covalent bond formation, like strain, like proximity, like acid-base interaction. So all of these we have read in the last session. Understood? So activation energy is that energy that is required for the formation of the transition state. And if this state is reached, it is stabilized by the enzyme that is in the system. Therefore, the enzyme lowers the activation energy required for a reaction. That means even with a lesser amount of energy, the reaction can proceed in the presence of an enzyme, which it would not have proceeded had the enzyme not been there in the first place. Okay, now for a normal reaction, that does maybe they have an enzyme coupled or not coupled, or catalyst associated or not associated, just a normal reaction, it is affected by a few factors. Okay, now what determines that is the kinetic theory or the collision theory. This kinetic theory or the collision theory states that when for two molecules to react, okay, suppose this molecule and another molecule has to react together, they have to react together. What are the prerequisites? One is that they must come near to each other, that much near that they are within bond forming distance. So they have come this near. Now there can be exchange of electrons, and the bond forming distance has been achieved. So they have to be within bond forming distance. They cannot be far away distant. So if there has to be a bond between you and someone else, you guys need to meet, you guys need to be friends with each other. It cannot happen like you don't know someone's situated at the other side of the on the other side of the earth. You cannot form a bond with them unless until you are within the bond forming distance. In the same way, in if you're talking about these molecules, you need to be close together within the bond forming distance, such that exchange of electrons or whatever covalent interactions can take place and bonds are formed. Okay, the second is that these molecules must possess enough kinetic energy to overcome the energy barrier required to reach the transition state. And what is this energy barrier to reach the transition state? This is the activation energy. So these molecules must possess energy equal to or more than the activation energy. Okay. Now, conditions that affect either the frequency of this collision or the energy of this collision will, or both, will increase or decrease the rate. Okay, so suppose if they increase the frequency of collision, that is, the bonds are, the molecules are so near each other that the frequency of their collision increases. That means then more bonds will be formed. Okay, then the rate of reaction will increase. Similarly, if the energy in the molecules increases to much more, then the rate of the reaction is going to increase. Got it? So these are the factors affecting the rate of the reaction. Temperature. Temperature and increase in temperature, the thermal energy is going to get converted to, thermal energy will get converted to the kinetic energy of the molecules. Okay, and the thermal energy is going to raise the kinetic energy of molecules. There will be more frequent collisions. Okay, one other way is the temperature is going to raise the it is going to raise the energy, and also it is going to raise the collision. It is going to raise the nearness of the molecules. Okay, the molecules are going, because they are now, they have a lot of kinetic energy, so then they are going to be very near to each other, because they will be the energy is making them move about. So there will be a lot of collisions, and the collisions are going to be high energy collisions, because they will have a lot of pent up energy inside because of the increase in temperature. So increase in temperature is going to increase the rate of a reaction. Okay, now this, for this temperature, we are going to draw an energy barrier diagram. Okay, now suppose, okay, suppose this is the energy barrier. That means this much energy has to be required by the molecules to proceed with the bond formation. Okay, in this reaction. So this is the energy barrier. This is the energy barrier. Right, this is the energy barrier. Now what will happen is the number of molecules possessing this much energy, we are going to plot. Okay, this is the number of molecules here. Now suppose the number of molecules possessing this energy is less than the barrier. Will the reaction proceed? No. Now suppose the number of molecules possessing the energy has just about reached the barrier. Now is the state when the reaction is just going to proceed. And when the molecules, all of the molecules have crossed this energy barrier, the reaction is going to successfully take place. Got it? So this is what the energy barrier diagram is. So you can, whenever you're mentioning the temperature, how temperature affects the rate of a reaction, be it an enzyme coupled reaction or a non-enzyme coupled reaction, a general reaction, then you have to draw this enzyme energy barrier diagram. Okay, I hope this one is clear to you. It is not hidden by my face. So it is like this. Got it? This is the third one. Understood? Okay. Now, the second thing was the concentration of the reactant, right? The second thing was the reactant concentration. Now, if the reactants are more in number, then there will be a the increase in the frequency of collision, right? If you're situated, if 10 people are there in a 5 by 5 room compared to 10 people being there in a 1 by 1 room, of course it will be more congested. So more congested means they're going to fight with each other. There'll be a lot of collisions, right? So 10 people staying in a 1 BHK or 10 people staying in a 10 BHK, the frequency of them meeting more or colliding more is going to be in a 1 BHK, right? So that is why the concentration of reactants is going to increase the frequency of collision. Okay, so this is also directly proportional. Okay, now how is it proportional? See, the rate of a reaction is directly proportional to the concentration of the reactants. Say reactants are A and B, so rate is directly proportional to A and B. Okay, now suppose the number of molecules of A and B are N and M respectively. So the rate is directly proportional to, suppose N molecules of A combine with M molecules of B to form the product. Okay, now the rate of this reaction will be directly proportional to the square of the stoichiometric indices of the reactant. Stoichiometry is balancing the chemical equation. This also we read in the last session. So you balance a chemical equation, balancing the chemical equation we have learned since class 8th. So balancing, you have to put in the numbers in number of molecules in front of the reactant, right? So these are the stoichiometric indices, N, M, whatever, maybe 2, 3, 1, whatever. So the number of molecules of the reactants that are reacting, those are the stoichiometric indices in this chemical formula, in this balanced equation. So the rate of this reaction is going to be a factor of their stoichiometric indices. So suppose one molecule of A is combining with two molecules of B to produce the product, then rate will be directly proportional to A to the power 1 and B to the power 2. Got it? Understood? So if the the concentration of B is doubled and the concentration of A is doubled, then the rate will be increased fourfold, right? So it will be 2 into 2. Understood? If the concentration for, so the rate at which the factor by which the rate increases or decreases is a multiple of all the substrates, increase in the concentration of all the substrates. Okay, so this is how you represent it. Understood? So if you remove this proportionality symbol, you're going to come up with rate is equal to K into A to the power N, B to the power M. Now if you focus at this subscript, what is 1 and what is minus 1? So rate 1 is the rate of formation of the product, and rate minus 1 is the rate of formation or disintegration of the product back to the substrates. Because another thing which we realized in the last session was almost all reactions are intrinsically reversible reactions. Almost all reactions are intrinsically reversible reactions depending upon the thermodynamic suitability or thermodynamic factors that are favoring a reaction to proceed in a particular direction. They can be irreversible. So suppose this product is getting formed and it is getting utilized by another reaction, or it is getting exhaled out, then this reaction will be irreversible because this product, then it is getting consumed, so it cannot go back to produce the substrate. But otherwise, all reactions are intrinsically irreversible. All reactions are intrinsically reversible. They have this bidirectional sign. Okay, so the rate of formation, that is rate of going in the right direction from the substrate to the product, is R1, and rate going backwards is -1. Rate -1. Understood? So of course, this, for this reaction, the sorry, not 2, it is -1. K -1. So for this reaction, the substrate will definitely be the products, because it is converting from product to the reactant. That is why for this reaction, the rate is going to depend upon the concentration of the products. So for any reaction, the rate is directly proportional to the concentration of the substrates. Understood? Now, what is the order of reaction? Order of reaction is the stoichiometric coefficient of a reactant, and it defines the order with respect to that reactant. Understood? So the order of this reaction for substrate A, for reactant A, is N, and the order of reaction for substrate B is M, and the order of reaction for this entire reaction, is N plus M. Understood? This is about the order of reaction. Okay, so you can define it with respect to the reactants, or you can define the order of the reaction per se. You have to focus on the stoichiometric coefficient. That is why it is extremely important to always write a balanced chemical reaction and not just a generic reaction. Okay, because it is very important to see how many molecules are reacting to produce different products. Now, what are pseudo first order reactions? There is something called pseudo first order reactions which are very helpful in enzyme assays and in conducting a lot of experiments related to enzyme kinetics. Pseudo means, as the name suggests, pseudo is false. First order reaction means the stoichiometric coefficient of all the reactants is going to be 1 here. Now, if you maintain the pseudo first order reactions, focus on one reactant. Okay, suppose this is the reaction. Suppose this is the reaction. Okay, and it forms this product. Okay, now this is the stoichiometric coefficient of A, this is the stoichiometric coefficient of B. Now, if you maintain the concentration of all other reactants as constant and you study the concentration of one of the reactants and you study its effect in the laboratory, then that reaction or that condition is going to be a pseudo first order condition for this reactant, because suppose you're going to maintain the concentration of B as such, you're not going to affect the concentration of B, the concentration of B is going to be constant, and you're going to change the concentration of A, or you're going to put in a lot of temperature changes, or you're going to introduce some other reactant, or you're going to introduce some pH changes, or you're going to introduce some pressure changes, and you're going to see how it affects the rate of this reaction, then that condition is going to be a pseudo first order condition. Why? Because the rate of the concentration of the other reactants of this reactant is artificially maintained as constant, and constant for a constant means the change or rate of change in this is 0. So if the rate of change for this is 0, there is no rate of change, then this is going to be 1. Okay, it is going to be, there's no rate of change, then it is not going to affect the rate of the overall reaction or the order of the overall reaction. And what is going to affect the order of the overall reaction? It is going to be the concentration or the order of this reactant which we are studying. So to study a particular various conditions affecting a particular reactant, we need to place them under pseudo first order conditions. Okay, understood? Next, what is K equilibrium? This is the ratio of rate constants. Okay, ratio of rate constants. Which rate constants? Rate constant of the forward reaction, that is conversion of substrate to products, that is K1, upon conversion of products to substrates, K minus 1. Got it? So this is the ratio of rate constants, that is A plus B is going to produce the product. This is the first, so this is the K1 and this is K minus 1. So K1 upon K minus 1 is equal to K equilibrium. At equilibrium, the rate of conversion of A and B to products is equal to the rate of conversion of products back to A and B. Okay, so they are existing in a dynamic equilibrium. That is, A and B are getting converted to P and P is getting converted to A and B, and the ratio of the concentration of substrates and products is equal. Okay, it is the same. So K1, the rate of formation, is going to be the same. So rate of formation of products is equal to the rate of conversion of products back to reactants. Huh? So that means what was K1? So if you write it like this, rate 1 is equal to K1 into, K1 into A to the power N and B to the power M. Rate minus 1 is K minus 1 into P ka concentration. Okay. Now, K1 by K minus 1 is equal to, when rate 1 is equal to rate minus 1, that means K1 into A to the power N. So, all these mathematical equations are going to be very easy if you understand the concept. Agreed? If at equilibrium, rate 1 is equal to rate minus 1. Therefore, K1 A to the power N B to the power M is equal to K minus 1 into product. Okay. Now, K equilibrium is what? K1 upon K minus 1. So, you cross multiply it like this. What will happen is P upon A to the power N B to the power M. So, this is what is K equilibrium. So if you have to write the formula for K equilibrium is the ratio of rate constant. It is going to be the concentration of products divided by the concentration of the reactants to the power their stoichiometric coefficient. Understood? This is what the ratio of rate constants is. At equilibrium, the rate of forward reaction is equal to the rate of backward reaction. Okay, rate of conversion of substrates to products is equal to the rate of conversion of products back to the substrates. What are the properties of this equilibrium constant? Equilibrium constant is the ratio of the reaction rate constants and not the rates. So it is not R1 upon R2, rather it is K1 upon R1 upon R minus 1, rather it is K1 upon K minus 1. This is very, very important. It is K1 upon K minus 1 and not R1 upon R minus 1. At equilibrium, the reaction rates and not the rate constant of the forward and backward reactions are the same. So please be very clear what you are writing, rate or rate constant. It is going to get you either full marks or 0 marks. Okay. So at equilibrium, the rates are constant. At equilibrium, what is equilibrium constant? It is the ratio of rate constants. So wherever you are coming across constant, equilibrium constant, it is the ratio of rate constants. Whenever you're not coming across constants, that is equilibrium. So at equilibrium, the reaction rates are equal. So if at all you're coming across constants in the question, then only your answer should have constant in the answer. So this is a general mnemonic. The numeric value of the equilibrium constant can be calculated either from the rate constants or from the concentration of the substrates and products. Very easy. The numeric value of the equilibrium constant can be calculated either from the equilibrium constants here. So Ke can either be K1 upon K minus 1 or Ke, that is equilibrium constant, can either be calculated from the concentration of products to the concentration of the reactants. Concentration of P upon concentration of A into B with their respective stoichiometric indices. Understood? So this is the third property of equilibrium constant. The fourth one, which is which is kind of a theoretical one, is equilibrium is a dynamic state. So it is not like A and B have converted to P and P is converting back to A. The same molecules are doing this. No, it is like you read about evergreen trees. So in evergreen trees, there it is not like all the leaves are green throughout the year and those are the same leaves. No, the tree keeps on shedding leaves and the tree keeps on growing leaves such that it is never bare. Okay, it always bears leaves and the tree is never devoid of leaves. But the leaves keep on recycling. Similarly, in this equilibrium, which is a dynamic state, there is no net change in the concentration of substrates and products, but they are individually, the molecules are continuously being interconverted. So A and B, the molecules of A and B are continuously forming P, and the molecules of P are continuously going back to again to convert to A and B. But these molecules are different. It is not like the same molecules are dancing. Okay, so the substrate is the same, the product is the same, but the molecules are continuously getting recycled and replenished. It is akin to or analogous to the example of an evergreen tree, where the leaves are not the same throughout the year, but the tree is green throughout the year. So the tree is in equilibrium throughout the year, but the leaves keep on shedding and new leaves keep on growing, such that the tree is never bare or naked. Okay, similarly, so the tree is also in a state of dynamic equilibrium. So everything is going about, motion is happening, but nothing is visible to the eye, because the rate of formation of the products is same as the rate of formation of its reconversion back to the reactants. So these are the four very important properties of equilibrium constant, which you should be aware of. Okay. Next comes, so now we have understood about the rates affecting a normal reaction. Now the equilibrium constant, what is the equilibrium, what affects the rate of a reaction, what affects the rate constant, what affects the equilibrium constant, what is the rate of a forward reaction, what is the rate of the backward reaction, what is the order of a reaction, what is the activation energy, temperature and reactant concentration, how do they affect the rate of a reaction. Now we come to an enzyme catalyzed reaction. So what are the kinetics of an enzyme catalyzed reaction? Enzymes, as we have seen, enzymes, the one basic concept is enzymes lower the activation energy barrier for a reaction. Activation energy barrier is the energy required to reach the transient state intermediate. So enzymes are going to lower this energy barrier, and now the energy required to reach this transient state intermediate is much lesser compared to without the enzyme. So if you see this reaction, this is the energy barrier. What enzyme will do is it is going to decrease this energy barrier, reduce this energy barrier to maybe here, so that this reaction can also take place and this reaction can also take place along with this reaction. So earlier only this reaction was occurring, because all the molecules had energy more than the activation energy or the energy barrier. Now an enzyme is going to lower the energy barrier. And how does it lower the energy barrier? The substrate binds at the active site of the enzyme, right? So there are a few forces, or there are some changes in the active site whenever a substrate binds. We read it in the last session, how the binding of the substrate to the active site brings about a conformational change in both the enzyme and the substrate. So a conformational change will be there in the enzyme, which in turn is going to introduce a conformational change in the substrate. And what was this model? It was the induced fit model of Koshland. Induced fit model of Koshland. This we read in the last session. So whenever a substrate binds to the active site of an enzyme, there is going to be a conformational change in the enzyme, which brings about a conformational change in the substrate. And this environment of the active site is isolated from the surrounding environment. So this is what stabilizes the intermediate that is formed here. The environment, it isolates it. The environment of the activation site isolates it from the surrounding environment and brings about a conformational change, thereby lowering the activation energy. Now, what happens is the transient state intermediate that is formed is stabilized by the enzyme. Okay, and how is it stabilized? There were four mechanisms which we read. One is by strain, that is the enzyme brings about, suppose this is the enzyme, Okay, and this is the substrate. So the substrate was earlier suppose like this. Now the substrate after binding to the enzyme has, see, there's a strain here because of its twisting. Now because of the pull, or because of physical or maybe chemical electrostatic repulsion forces, what happens is there is a strain in the covalent forces on the covalent bonds of the substrate, and the force required to break the bonds decreases. Therefore activation energy decreases. Proximity, how more molecules will be, the reactants will be brought in together, close together, so therefore the kinetic energy will increase, their proximity will increase, the bond forming distance will decrease, and the bonds will form much easily, the rate of the reaction is going to increase. Covalent catalysis, that is formation of covalent bonds with each other. So this also is done by enzymes, the formation. So covalent bonds are broken by strain and covalent bonds are formed here, covalent catalysis. The last was acid base reactions, where the enzyme behaves as Lewis acid or Lewis base. By acid will accept electrons, acid accepts lone pair of electrons, and base, Lewis base, is going to donate lone pair of electrons. Acid donates proton and base accepts proton. These concepts should be on your fingertips. They should be so clear to you that even in your sleep, if someone wakes you up, you should know Lewis acid will accept electron, Lewis acid will donate proton. Okay, understood this? Now, one very important thing is that enzymes affect the rate of a reaction by lowering the activation energy barrier, but enzymes do not affect the equilibrium constant. The equilibrium constant is not affected. The rate of a reaction is definitely affected, but the equilibrium constant is not affected. So what was the equilibrium constant? If you see, the equilibrium constant depended on the concentration of the products and the concentration of the reactants. Enzyme is neither a reactant nor a product. Okay, so enzyme appears unscathed or unmodified after the reaction is over. So the enzyme can neither be counted as a reactant or as a product. And the equilibrium constant, it depends upon the ratio of the product and the ratio of the concentration of the product to the reactants. So the equilibrium constant is independent of the concentration of the enzyme. Extremely important point. If at all you get an MCQ stating what does the enzyme do to the equilibrium constant, increase, decrease, do whatever, it does not affect the equilibrium constant. Please be clear with it, okay? Because the equilibrium constant depends upon the concentration of the products and the reactants, whereas the enzyme does not participate in the reaction as a reactant or a product. Okay, got it? Next. So what are the factors affecting the rate of enzyme catalyzed reactions? Temperature, just like temperature affects a normal reaction, it is going to affect an enzyme catalyzed reaction. But here what will happen is, if you increase the temperature, the rate of reaction is going to increase. Why? Because increase in temperature is going to put in more kinetic energy. So the rate of the collision, according to the kinetic theory, the rate of collision is going to increase. More frequent high energy collisions are going to occur between the molecules. So the rate of reaction is going to increase till the time that denaturation of enzyme does not take place. Because in the end, the enzyme is a protein. Okay, so proteins are formed of secondary and tertiary conformations of a polypeptide chain. Now, proteins are subject to denaturation, that is breaking or untwisting or degrading of the polypeptide chain. The polypeptide chain reduces back to the amino acids. Okay, the polypeptide chain is going to untwist. The alpha helix is going to break down. The beta pleated sheets are going to break down back to the primary structure because of increase in temperature. So at a particular, beyond a particular temperature, the enzyme itself is going to denature. The covalent bonds in the enzyme itself is going to are itself going to break down, and then the temperature, then the rate of the reaction is going to decrease. Okay, so in the human body, about a temperature of about 45 to 55 degrees Celsius is tolerable. Okay, so till about 55 degrees Celsius, the enzymes can work. But in conditions like hyperthermia or malignant hyperthermia, when the temperature increases so much that the enzymes required for normal bodily activities get denatured, it can turn fatal. Okay, therefore, the rate of an enzyme catalyzed reaction for it, the temperature to affect it is different, how it affects it. Okay, now what is the temperature coefficient? Temperature coefficient, which you denote by Q10, Q and a subscript of 10. Q10 is a factor by which the rate of a biologic reaction increases for a 10 degree Celsius increase in temperature. So if you increase the temperature by 10 degrees Celsius, how much is the reaction going to change? So initially it is going to, the rate of the reaction is going to increase, but after the enzymes get denatured, then the rate of the reaction is going to decrease. Okay, so this is how temperature affects the enzyme catalyzed reactions. Hydrogen ion concentration. What is hydrogen ion concentration? It is pH, right? Negative logarithm of hydrogen ion concentration is the pH of the solution. So pH is acidity or alkalinity of the solution. Every enzyme catalyzed reaction requires an optimal activity for its optimal pH for its activity. For the enzymes inside the human body, the optimal pH is around 5 to 9. Okay, so, if at all there is a change in the pH, then what happens is the enzymes may or may not function properly. So, enzymes, you know how they are functioning by acid-base catalysis, right? So, there, the amino group or the COOH group in the polypeptide chain, they can themselves get changed, or they can themselves get metabolized during a change, a drastic change in the pH of the environment. So the enzyme itself can get affected. Okay, therefore the enzyme catalyzed reaction will be affected beyond this optimal pH. So there has to be an optimal temperature and there has to be an optimal pH for the enzymes inside the body to function normally, to function optimally. Okay, the next is the substrate concentration. So for a normal reaction, we saw how increase in the concentration of substrates is going to increase the rate of the reaction. Okay, so how this is what we learned here, what the rate constant was, right? So reactant concentration directly, it is directly proportional to the frequency of collision of reactants, and it the rate of the reaction is also directly proportional to the rate of the to the concentration of the reactants. What happens in an enzyme catalyzed reaction? Now, the initial velocity, initially the rate of the enzyme catalyzed reaction is going to increase with an increase in the substrate concentration, but, a big but, only till a particular limit. After that, the rate is going to get plateaued, or it is going to get stabilized. It is not, if you increase the substrate concentration beyond that limit, there is going to be no change in the rate of the reaction. This is different from the rate of a normal reaction, where the rate of the reaction is directly proportional. No matter how much you raise the concentration, the rate of the reaction is going to increase. But in an enzyme catalyzed reaction, the substrate concentration directly affects the rate of the reaction only till a particular limit. After that limit, even if you increase the substrate concentration by no matter how many factors, the rate of the reaction is not going to increase. Okay, so there's an initial velocity of the reaction that is measured at the start of a reaction, VI, and there is a maximum velocity of the reaction, that is, this is the maximum velocity that the reaction can attain, And after that, the velocity of the reaction is not going to increase no matter how much you raise the concentration of the substrate. So initial velocity increases with the substrate concentration till you attain Vmax, after which the velocity plateaus. Now, why is it so? Okay, the enzyme, now suppose this is the enzyme present in the solution. Okay, so these are the enzymes. Okay, now what happens is, suppose these three enzymes are there. Now you have just one substrate. Okay, now this substrate is going to attach to this enzyme. Okay, so this is the initial velocity of the reaction. Now you increase the substrate concentration, one more substrate has entered. Now this is also going to attach here. Now the velocity has increased. Now you increase the substrate concentration, this is going to attach here. So all the active sites of all the enzymes are now saturated. All the enzymes are now bound to the substrate, and an enzyme substrate complex is formed. Now this enzyme substrate complex, this is the transient intermediate. This is stabilized. Now this enzyme substrate complex is going to produce the enzyme and product. And after the product is formed, the product is going to detach itself or release itself from the active site of the enzyme. Only then will the active site be again free, and the rest of the substrates can then attach to the enzyme active site. So now once you introduce one more substrate or two more substrates in the system, they have nowhere to attach to. There are no more enzyme molecules to attach to for the substrate. So the rate of the reaction at this saturation stage, where all the enzyme molecules are saturated with the substrate and the transient intermediate is formed, this is the rate of Vmax, that is maximum velocity. That is the rate of the reaction at this stage. Now it is not going to increase further till the time that all these substrates are metabolized to produce the product and the active sites are free. Understood? Therefore, Vmax is reached because of saturation kinetics. That is, enzyme saturates. Saturation kinetics. The active site of the enzymes have saturated. Okay. Now the shape of this curve is going to be hyperbolic. How do we describe it? See. This is the enzyme. Okay. This is the concentration. You denote it by K, the concentration of the substrates, and this is the velocity, okay, V. So this is the rate of the reaction compared to the concentration of the substrates of the reactants. Okay, how the concentration of the substrates affects the rate of the reaction in an enzyme catalyzed reaction. Now, as the concentration of the substrates increases, the rate is increasing till a particular point where it has reached the maximum, which is Vmax. So what kind of a curve is this? This is a hyperbolic curve. Remember the curve of oxygen dissociation curve of myoglobin? That was also a hyperbolic curve. Okay. So this is a hyperbolic curve where this Vmax is reached, and now the rate of the reaction is not going to change. Okay, sorry, this was V and this is K. This is the velocity and this is the concentration. So this is the maximum velocity which has reached, and after this the velocity is not going to change. Now, if you half this velocity, what is the half? Suppose this was the Vmax here. The half of Vmax here is Vmax by 2. This is Vmax by 2. So the concentration of the substrates at Vmax by 2 is Km. This we are going to read later on in the Michaelis-Menten equation. Okay, what is Km? It is the concentration of the substrates at which the rate of the reaction reaches half of the maximum possible velocity of that reaction for a particular concentration of enzyme. The entire definition is very important. For a particular concentration of enzyme is very important, because if you increase the concentration of enzyme, there will be more active sites available. So if there is just these three enzymes, then the half of Vmax is this, and the concentration of the reactants required to reach this half of the velocity, maximum velocity, is Km. So Km is the substrate concentration required to reach half of the maximum possible velocity of this reaction at a particular enzyme concentration. This is the full definition of Km. Okay. So Michaelis-Menten equation denotes the relationship between velocity of a reaction and the substrate concentration. This graph you should know. Okay, now if you're increasing, suppose you're going from this point to this point A to point B. So increasing the substrate concentration is going to increase the velocity from point A to point B. But suppose you're increasing the substrate concentration from point B to point C, nothing is going to happen on the velocity. Why? Because all the active sites of the enzymes are saturated now. There are no more molecules of enzymes available to bind to the substrate. Understood? So this graph should be extremely clear to all of you. The rate of change of a reaction, the rate of progress of a reaction to the concentration of the substrates in an enzyme catalyzed reaction. The shape is that of a hyperbola. Next, we have to mathematically represent it as a Michaelis-Menten equation. The Michaelis-Menten equation denotes the relationship between the velocity of a reaction and the substrate concentration in an enzyme catalyzed reaction. Okay. Now, what is the Michaelis-Menten equation? It is Vi, or the initial velocity, is equal to Vmax into the substrate concentration upon Km plus the substrate concentration. This is the Michaelis-Menten equation. The Michaelis-Menten equation. It denotes the relationship between the velocity of a reaction and the substrate concentration in an enzyme catalyzed reaction. How do you mathematically represent it? The initial velocity of a reaction is equal to the maximum attainable velocity of that reaction at a particular enzyme concentration multiplied by the substrate concentration at that particular time, divided by the substrate concentration at which the half of the maximum possible velocity for that reaction is attained for a given enzyme concentration, plus the substrate concentration at that particular moment. Okay, now if you have to write this Michaelis-Menten equation when the substrate concentration is much less than the Km. Km is also a substrate concentration only, right? Km is also concentration, right? It is a type of substrate concentration, a point in substrate concentration. So when the substrate concentration is very less compared to Km, then this S, this here, it can be negligible compared to Km. Understood? So how do you write it? You write it as Vi is equal to Vmax upon, because this is very negligible compared to this, so this is Km. So when, and now when so we are going to write each and everything, and then we are going to discuss what it means. When the substrate concentration is equal to Km, how do we write it? When the substrate concentration is equal to Km, how do we write it? Vi, or the velocity of the reaction, is, it will be S. So equal to Km, you can write Km is equal to S. So S plus S is what? 2S. It will be V max S upon 2S. You cut it, it will be V max by 2. When the substrate concentration is equal to Km, the velocity is V max by 2. What is this? Km is the substrate concentration at which the velocity is V max by 2. So this is the graphical thing is represented mathematically here. When the substrate concentration is much more than Km, then Vi is equal to V max substrate upon, now Km you don't write because it is negligible. This will get cancelled. So Vi is equal to V max. So when the substrate concentration is much more than Km, then Vi is equal to V max. Okay, when the substrate concentration is equal to Km, then the Vi is equal to V max by 2. Okay, and when the substrate concentration is much less than Km, then the velocity is V max by Km. Okay, so it will be the initial velocity when it is much less than Km. So here, right? Understood? It is V max. So S, you're avoiding it. You don't want to write S, right? So what happens is S is very much less than Km. So it is V max by Km. Understood this? This is extremely, extremely important. Okay, how we are going to write it. Okay, all these things are very, very important. Next, what is the catalytic constant? Okay, so we know the reaction coefficient. We have understood the equilibrium constant. We know the rate constant. Now, what is the catalytic constant? That is K cat. What is the catalytic constant? Catalytic constant is V max. That is the maximum possible attainable velocity divided by the number of active sites on the enzyme. Okay, so the maximum attainable velocity divided by the number of active sites on the enzyme is the catalytic constant of the enzyme, of the reaction. And what is the catalytic efficiency? It is the catalytic constant divided by the Km. Okay, so catalytic efficiency is a ratio of constants. So if the Km is lesser, the catalytic efficiency is higher. That is, at a lesser substrate concentration, if half the maximum velocity is reached, that means the catalytic efficiency is very high. Understood? So if at a lesser concentration of substrate, the half of the maximum velocity is getting reached, that means the catalytic efficiency is very high. So catalytic efficiency is catalytic constant divided by the Km, that is the substrate concentration at which the maximum possible velocity is half, the half of the maximum possible velocity is reached, and catalytic constant is V max divided by the number of active sites on that particular enzyme. Okay, very, very important, Michaelis-Menten equation. Okay, V max into S upon Km plus S. Okay, so you should know the Michaelis-Menten equation. You should know how this enzyme velocity by substrate concentration curve it works. So this is extremely, extremely important for you guys. Okay, understood? I hope this is clear to you. I hope you know how to draw this curve. Okay. So this here V max upon if substrate is equal, yeah, so V max upon Km, this is almost equal to Vi, or the initial velocity only. So this means what happens, that is the starting of the reaction. That means if the substrate concentration is very less than Km, that means it is around the start of the reaction here. The velocity is near the initial velocity. Okay, it is near about the initial velocity of the reaction. Now comes the Hill equation. Now, till now we were reading about the normal enzyme kinetics. Now comes cooperative binding. Where have we heard of cooperative binding? We have heard of cooperative binding in the chapter on hemoglobin and myoglobin. So hemoglobin, being a tetramer, it is a four molecule compound, right? There are four molecules combining together to form one molecule of hemoglobin, right? Now what happens in hemoglobin, one molecule of oxygen, once it attaches, the rest of the molecules of oxygen will bind to it in a cooperative fashion. That means the affinity for the other molecules of oxygen is going to increase. Once one molecule of oxygen is bound to hemoglobin molecule, the affinity for the other molecules is going to increase. This is what is cooperative binding. So there are enzymes that exhibit this cooperative binding. Most enzymes will display saturation kinetics. That means when once their active sites are occupied, then the Vmax is going to be reached, and this is how the Michaelis-Menten expression will be there. But there will be some enzymes where the substrates will bind in a cooperative fashion. That is, once one substrate is bound to the enzyme, the affinity for the other substrates is going to increase by many fold. It is going to increase to more than the affinity for that particular the first substrate molecule. But this is the exclusive property of multimeric enzymes, that is enzymes possessing two or more molecules. Okay, this is the exclusive property of multimeric enzymes, which have more than two or more molecules, will have multiple active sites. Multiple active sites. Okay, since they will have multiple active sites, multimeric is active site is a quaternary structure. So since if they have multiple active sites, more than one active sites, or once a substrate binds to one active site, the affinity for the substrate to bind at the other active site is going to increase. Now, we discussed how the oxy-myoglobin dissociation curve was a hyperbola. Similarly, the saturation kinetics was a hyperbola. Here, the saturation kinetics is a hyperbola. Now, the oxyhemoglobin dissociation curve was sigmoid. Similarly, the Hill for multimeric enzymes cooperative binding, the curve for rate to velocity is sigmoid, like this. Okay, so this is a sigmoid curve. It is represented by the Hill equation, and it represents cooperative binding, whereas saturation kinetics is denoted by the Michaelis-Menten expression, and it is a hyperbolic curve, and it displays saturation kinetics. Understood? So these were most of the topics of enzyme kinetics that we should know. They should be extremely clear to all of us. Okay, these topics. Next comes regulation of activity, where inhibition of enzyme activity is what we are reading. Okay. Now, in the last session, we had read about transient state analogs. Now, these are compounds that look like, or they are structurally similar to the transient state intermediate. Now, what happens is they look like the transient state intermediate. If you introduce them in the environment, they are going to falsely signal the enzyme that so many transition state intermediates have been formed, and the reaction is going to slow down, or it is going to get inhibited. Whereas in reality, they are non-functional or bogus analogs or bogus molecules. They are not going to proceed, they are functionally inactive. They're not going to proceed the reaction further. Okay, so this is what the role of an inhibitor is. So there can be either competitive inhibitors or non-competitive inhibitors. Non-competitive may there can be either simple non-competitive inhibitors or complex non-competitive inhibitors. So for competitive inhibitor, now who is your competitor? You are not going to compete. You being in MBBS are not going to go and compete with a person in the in standard 9, or a person studying in class first, or for that matter, you are not going to go and compete with a PhD holder, or you're not going to go and compete with your professors. So you are going to compete with someone who is similar in your situation, who is present in your situation, or who is similar to you, right? In the same class also, many of you may or may not possess the same level of preparation. So you may consider someone as your competitor who who gets the same marks as you, or whose level of thinking or whose way of thinking is almost the same as you, who can memorize lessons, or who understands the lessons in the same way, similar way as you. So a person who is very much similar to you poses the maximum competition to you. This is very natural. You are not going to compete with someone who is dissimilar to you, because there has to be some scale of competition. Therefore, a competitive inhibitor will resemble the substrate. Okay, something that resembles functionally is an analog. Something that resembles structurally is a homolog. Okay, now competitive inhibitors, they resemble the substrates. They resemble them in their function. That is, they go and bind to the enzyme active site. Competitive inhibitors resemble the substrates. An example is, if you have seen my video on the Krebs cycle, how I have simplified the Krebs cycle using a story. So there we saw how oxaloacetate combines with acetyl-CoA, okay, to form citrate. Now citrate changes to cis-aconitate, changes to isocitrate. Isocitrate changes to oxalosuccinate. It changes to alpha ketoglutarate. It changes to succinyl CoA. Succinyl CoA changes to succinate. Succinate changes to fumarate. Fumarate changes to malate, and malate then replenishes oxaloacetate to then continue this cycle. Now this step where succinate changes to fumarate, this step here FADH2 is produced. This is flavin, it uses flavin, okay, flavin adenine dihydrogen. This FADH2 is produced here from a conversion of succinate to fumarate, and the enzyme involved here is succinate dehydrogenase. Now what is the substrate for this enzyme? The substrate is succinate, the product is fumarate. Now suppose this is succinate dehydrogenase enzyme, okay? This is succinate dehydrogenase enzyme, and this is its active site, okay? Now on this site, succinate is going to bind, and once succinate binds on this site, it produces fumarate, okay? Now suppose this is how succinate looks like. Okay, this is how succinate looks like. The succinate is supposed to come and bind here like this. Now, a competitor of succinate has entered the environment. How does the competitor look? The competitor looks like this. It is similar as succinate. Now what will happen is it is going to go and attach here. Now this enzyme is going to form an enzyme inhibitor complex. Instead of an enzyme substrate complex, it is going to form an enzyme inhibitor complex. Now why is it so that it is getting attached to the inhibitor and not to the substrate? It can be due to two reasons. One is that either the concentration of this is more, either the concentration of the inhibitor is more, or the affinity of the enzyme to the inhibitor is more. If the enzyme likes this more, then it is going to get attached to the inhibitor compared to this substrate. Or if multiple inhibitors are present in the environment and only a few molecules of substrate are present in the environment, then also they are going to crowd near the active site and occupy it. Okay, so there are two reasons why a competitive inhibitor beats this substrate. So here in this example, this is malonate and this is succinate, and this is the succinate dehydrogenase enzyme. Malonate goes and sits here and it stops this reaction at this step. So this Krebs cycle is competitively inhibited by malonate, which competes against succinate for the active site of the enzyme succinate dehydrogenase. Okay, now this competitive inhibitor acts by decreasing the number of free enzymes, because this enzyme is now not free. By decreasing the number of free enzymes available to form the enzyme substrate complex. Remember, the enzyme substrate complex is the transient state which is essential to reach the activation energy barrier. It is very important to form the enzyme substrate complex, then only the activation energy barrier will be breached. Now, this enzyme substrate complex is not formed because all the enzymes are now occupied by the inhibitor to form the enzyme inhibitor complex. After forming the enzyme inhibitor complex, nothing is done. It stops. The reaction stops here. It does not go further. Understood? So increasing the concentration of the substrate will decrease the concentration of EI complex, and increasing the concentration of inhibitor will decrease the ES complex. This we saw. Whatever will be more in concentration is going to occupy this active site. The extent to which the substrate concentration must be increased to overcome the enzyme inhibitor complex formation. How much you have to increase the substrate concentration? How much should you increase this so that this is not formed? Now that will depend upon how much the enzyme loves the inhibitor, how much the enzyme loves the substrate, and how much is the concentration of the inhibitor. So all this game, this is a game of the concentration of the inhibitor versus the concentration of the substrate, and the affinity of the enzyme for the substrate versus the affinity of the enzyme for the inhibitor. If the enzyme likes the substrate more, then the concentration of the substrate should be will need to be increased only by a little to overcome the inhibitor. Okay, now suppose you like now suppose this there is this boy A who likes this girl B. Okay, now here comes another competitor for B, that is C. Okay, now A likes B, but B has annoyed A by doing something. A wanted chocolates from B, or A wanted some attention from B, but B has not given. This boy has not given a lot of attention to this girl A. Okay, now A is annoyed with B. Now she says, I'm very annoyed with you, but in her heart she likes B. She's in love with B, but outside she's showing that she's very annoyed with B because B has not gifted her B, for whatever reason. Okay, they can throw tantrums. We can throw tantrums. So here comes the opportunity. This C is another Majnu. He likes A. And he comes in and he says, he sees an opportunity. Okay, now I have an opportunity because A and B have had a fight. So now I can come and I can woo A. So C comes in. A does not like C inherently as much as she likes B, but C comes in with a lot of flowers, chocolates, and all. Okay, and C is again and again going around. So the concentration of C around A is increasing, but B is not going about A, going after A, because B is just sitting. B is not going after A. B is also khawing bhav. Okay. Now, once B sees that C is going after A a lot, the concentration of C is increasing around A, then B gets threatened. Now B says, okay, I also have to go. So B, even if C is running after A for so many days, but B just goes and looks at A and smiles and gets a chocolate, and then A ka dil pighal jata hai, and A goes to B and they form a bond. So A here is an enzyme. B here is the substrate for which the enzyme has a lot of affinity. And C here is the competitive inhibitor who is coming in to attach to the active site of enzyme. So if the concentration of the competitive inhibitor is increasing, so it can go and form a few bonds with A, but A ka heart lies with B only. So B ka thoda sa bhi concentration if you increase, it is going to successfully break the it is going to successfully inhibit this competitive inhibitor, and it is going to go back and form a bond with A. Now suppose this was the inhibitor and this was the substrate. Suppose enzyme had a lot of affinity for the inhibitor. Then C needed to get in a lot of chocolates, a lot of other gifts, a lot of attention, and it needed to be present about 24/7. Matlab, bahut efforts it needed to put in. So you need to increase the concentration of the substrate by many fold if the enzyme has more affinity for inhibitor. Understood? So this is what this line says. So it is all a game of affinity and concentration of the inhibitor and the substrate in competitive inhibition. Understood? Next, we come to non-competitive inhibitors. Non-competitive inhibitors, the simple non-competitive inhibitors, first, what will they do is, if you go back to this graph, the hyperbola, the non-competitive inhibitors are going to lower the Vmax. When they enter the system, they are going to lower the Vmax by maybe like this, but they are not going to affect the Km. Km is the property of the substrate. Km is the concentration of the substrate, and Vmax is the property of the reaction. So they are affecting the reaction, but they are not affecting the substrate. Now what happens is, this is the Km, the enzyme concentration at which half the maximum velocity is reached. So the Km is the same. This was Vmax for without inhibition, Vmax half without inhibition, and this is the half of Vmax with inhibition. Okay. So the Km is the same, the concentration of the substrate at which the half of the maximum velocity is reached is the same, but the half of the maximum velocity is reduced. That means that the overall velocity of the reaction is getting reduced. That means the overall reaction rate is going to reduce. The rate of the reaction is going to get reduced. Okay. Therefore, the non-competitive inhibitors, in simple non-competitive inhibition, there is no effect on the binding of the substrate. The substrate is going to normally bind the enzyme as it did. Unlike competitive inhibition, where the substrate binding is affected by the competitive inhibitor. Here it is going to normally form an enzyme substrate complex. But along with that, an inhibitor is also going to attach to this complex, and an enzyme inhibitor substrate complex is going to get formed. So even if an enzyme is attached to the inhibitor, even if EI is complex is formed, still the substrate can come and get attached to it. Still EIS complex can form in simple non-competitive inhibition. Whereas in competitive inhibition, if EI is formed, then S cannot get attached here because the active site is occupied. The enzyme is not free. Here, the inhibitor is not attaching at the active site, rather it is attaching at another site and inhibiting it. So the active site is free for the substrate to bind. So substrate can even bind to an enzyme inhibitor complex in simple non-competitive inhibition. All the properties of the substrate are the same, whereas the property of the reaction is affected. That is, Vmax is lowered, but Km is the same. Okay, the efficiency of this complex is reduced. What is affected? If Vmax is affected, then what will be affected? Catalytic efficiency. Why? Because catalytic efficiency, or Lcat, what was Kcat was what? Kcat was the catalytic coefficient, and catalytic efficiency is Kcat upon Km. And what was Kcat? Kcat was Vmax upon the active sites. So if Vmax is reduced, then the catalytic efficiency will be affected. Okay, so catalytic efficiency is affected, but the ability of the enzyme to form complex with the substrate is not affected in simple non-competitive inhibition. Okay, the binding site for this inhibitor does not bear any similarity generally to the active site where the substrate binds. Okay, now also one very important thing is the affinity of the enzyme for the substrate and the affinity of the enzyme inhibitor complex for the substrate is identical. That is, non-competitive inhibitors do not affect the affinity of the enzyme to the substrate. Very important. Okay, now there is something that is complex non-competitive inhibition, where these inhibitors also affect the affinity of the enzyme for the substrate. Okay, so here it has properties of competitive as well as non-competitive inhibition, but we're not going to discuss much of it. We just want to differentiate between simple non-competitive inhibition and competitive inhibition. Okay, what is IC50? It is the inhibitory potency of an inhibitor. How potent is an inhibitor is measured by IC50. It is the concentration of the inhibitor that produces 50% inhibition in the reaction. Concentration of the inhibitor that decreases the rate of the reaction by 50%. That reduces the rate of the reaction by half. Concentration of the inhibitor that produces 50% inhibition in the rate of the reaction. Okay, now there can be two types of inhibitions. One was, we saw how competitive and non-competitive inhibitors, how they are substrate analogs. Okay, they represent or they affect something called the substrate, or they affect something called the rate of the reaction. Now we have the mechanism based inhibition, which is also called suicide inhibition. Here what happens is, there were 4 mechanisms of enzyme action. Remember, catalysis by proximity, that is increasing the proximity between the molecules or reducing the distance between the molecules. Second was catalysis by strain, that is, there is a strain in the covalent forces of a molecule, so that the force or the energy required to break the bond is reduced, and it is the activation energy is reduced, and a transient state intermediate is formed. Okay, next is covalent catalysis. Is covalent bond formation occurs. Okay, next is, here covalent catalysis, which example we read, it was ping pong mechanism, right, of transamination. One amino acid comes in, the other follows, the first one goes away, an enzyme amino acid complex was getting formed. The enzyme was getting modified during the reaction, but then just after the reaction is complete, the enzyme goes out unmodified. So please go back to the last session if you're not understanding these terms, ping pong mechanism or ping pong reactions or transamination reactions, because all these we have read in the first session. And the last one was acid base mechanism. Okay, how Lewis acids and Lewis base, the enzyme, the R chains or the peptidyl chains on the enzyme, they behave as Lewis acids and Lewis bases. Okay, now what happens is, so if any of these four mechanisms of the enzymes are targeted by inhibitors, then that is what is known as mechanism based inhibition or suicide inhibition. Okay, now substrate analogs which contain a chemical, substrate analogs are what? Substrate analogs means they resemble the substrates. They resemble the substrates. Substrate analogs containing a chemical group that can be transformed by the catalytic machinery of the target enzymes. See, when we were reading about covalent catalysis or catalysis by strain, we came across as transient state analogs, right? What we read was these analogs, they are produced by pharmaceutical industries to resemble the substrate. They are substrate analogs that these transient state analogs resemble the transient state, and they affect the mechanism of mechanism of catalysis by strain. Okay, this transient state where the substrate is attached to the enzyme, that transient state analog is created artificially, and that analog is going to competitively inhibit the mechanism of catalysis by strain. Okay, so this is how these analogs act. Okay, now after binding the active site, catalysis by the enzymes generates a highly reactive group that forms a covalent bond and blocks the function of a catalytically essential residue. What happens is, suppose this is an enzyme and this has the active site here. Now, once these transient state analogs or the substrate analogs bind to this, there is a chemical change somewhere maybe here. Okay, there is a chemical change somewhere maybe here. And this is an important residue that was required to bring about a change in the substrate to form the product. So binding at one site is going to bring about a chemical change in another site of the enzyme, which is essential for catalysis. This is how this suicide inhibition acts. Suicide means binding on the same group or binding on this enzyme is going to kill this enzyme itself. Okay, so something that resembles this itself is going to bring about a negative change in its own molecule. This is why it is called suicide inhibition. Okay, understood? Now, what is the rate limiting reaction? What is a rate limiting reaction? A rate limiting step is that step which controls the overall reaction. Now, a reaction can have a lot of steps. That step whose property, that step whose presence or absence is going to dictate how the reaction is going to go, is what is called the rate limiting reaction. Okay, now suppose so if you see that this is maybe, so this is a traffic, okay, going about, this is a normal road, all the cars are going about like this normally they're going, okay, nothing is happening. Now suppose there is a small bottleneck here, that is the road is getting small, this is a bottleneck, that this is the neck of the bottle. Now what happens is, the rate at which the cars pass from here is the rate at which the cars are going to appear here when the road again becomes broad. So if you see that this is the car, this green car is coming here, this is leading on this road, and this black car is somewhat behind. So if you see from here, if you're seeing from here, from this end, you will see, you will think that okay, this is going to come out first here, but maybe this green car is going to come out first here. But what happens is, inside this bottleneck, this green car gets left behind and this black car overtakes. This black car has overtaken and this green car is left behind here. So what happens here in this bottleneck, what happens here in this bottleneck is going to determine the rate of this reaction, is going to determine the rate of this traffic. Okay, understood? uh, So this is how this rate limiting step proceeds. Okay. So what the catalytic efficiency of the reaction at the bottleneck, at the step, the catalytic efficiency of this rate limiting step is what is going to determine the rate of the overall reaction. Okay, the overall catalytic step, overall catalytic capacity or catalytic efficiency of the rate limiting step is what is going to determine the metabolic flux, or what is going to determine the rate of the overall reaction. Okay, now the catalytic capacity of this rate limiting step is the product, the catalytic capacity is the product of the concentration of the enzyme molecules and their intrinsic catalytic efficiency. The concentration of these cars and their efficiency, that is how efficiently, their mileage. Okay, so intrinsic catalytic efficiency of the molecules, that is how are these enzyme molecules, how efficient are these enzyme molecules, and their concentration, how many enzyme molecules are present. Okay, so these two factors determine the overall catalytic capacity of the reaction. And these two factors, then if they determine the overall catalytic capacity, then these can be targeted to control the enzyme reaction. Okay, so if you want to if you want to affect, or if you want to bring about a change in the enzyme catalyzed reaction, you have to target the rate limiting step, that is the bottleneck of the reaction where the enzyme is acting. And you have to either target the intrinsic capacity of the enzyme, or you have to target the enzyme concentration. Okay, so enzyme concentration is targeted. You can either control the enzyme synthesis by inducers. Now they are some kind of substrates or related products which stimulate the transcription of genes which code for enzymes. A classic example is the lac operon. Right? In lac operon in E. coli, what happens is, if you place the E. coli molecule in glucose, it will catabolize lactose, that is it is going to break down lactose only when there is a beta galactoside present. Beta galactoside is an inducer. A beta galactoside molecule, when it is present in the environment, only then will the lac operon start. So that is an inducer. That means it induces, or it stimulates the transcription of genes required for the enzyme to start working, or the enzyme to get produced. Okay, so the enzyme for breakdown of lactose is lactase, and that gets produced, that is beta galactosidase, and that gets produced only in the presence of the inducer. So beta galactosidase and galactoside permease, these enzymes are inducible enzymes because they have to be triggered by the presence of an inducer, that is the beta galactoside in the environment. In humans, the examples of inducers are HMG-CoA reductase enzyme, urea cycle enzymes, ALA synthase enzyme, cytochrome P450 enzyme. All these are inducible enzymes. Okay. Now there is something, if something is inducing, there is something that is repressor or repressing the synthesis of enzyme. That is any metabolite whose excess will curtail the synthesis of its cognate or respective enzyme. Okay. Understood? Next is control of intrinsic catalytic activity. So we have controlled the enzyme concentration. How? By inducer and by repressor. So how do you control the rate limiting step? By either controlling the enzyme concentration or by controlling the intrinsic catalytic capacity of the enzyme. So how do you control the enzyme concentration? By inducers or repressors. Now, how do you control the intrinsic catalytic efficiency? You control the intrinsic catalytic efficiency by either allosteric regulation or by covalent modification. Understood? I think now the whole of the chapter would be clear to you. So there are two ways in which you control the intrinsic catalytic efficiency, either by allosteric regulation or by covalent modification. So how do you control the rate limiting step of a reaction? We control the rate limiting step by controlling the catalytic capacity of the enzyme. How do you control the catalytic capacity of the enzyme? By either increasing or decreasing the enzyme synthesis and its concentration, or by increasing or decreasing the intrinsic catalytic efficiency of the enzyme. What was the intrinsic catalytic efficiency of the enzyme? Kcat. V max by St. Now catalytic efficiency was Kcat upon Km. Understood? Now, this intrinsic catalytic efficiency is affected by either allosteric inhibition, allosteric activity, or covalent modification. And enzyme concentration is affected by either inducers or repressors. So, this is the overall summary of your enzyme control. Okay? Understood? Now, what is allosteric regulation? Allosteric regulation is very, very important. Now, one thing which should be understood by you is this control of enzyme synthesis is a slow process. Induction and repression, inducing the enzyme synthesis or repressing the enzyme synthesis, is a slow process, whereas controlling the intrinsic catalytic efficiency of the available enzyme is a very fast process. Okay, allosteric regulation and covalent modification are very fast processes. Okay, now what are allosteric effectors? Allosteric effectors, they bind to the enzymes by non-covalent interactions. Okay, they have a separate site other than the active site for their binding, and once they bind to the enzyme, there is a change in its catalytic efficiency. Allosteric, allo and steric. Steric means in space, allo means different. So their binding site on the enzyme is different. Allosteric means what is this? In space, something related to the space. Allo means different. So these molecules, they bind at a different site on the enzyme other than the active site for the substrate in a non-covalent fashion, and they bring about a change in its intrinsic catalytic efficiency. Understood? The enzyme effector complex is a distinct molecular entity different from the individual enzyme and the individual effector. The enzyme effector complex becomes a different entity. Okay, so there are two individuals, the enzyme and the effector. Once they combine, they form an entity and they lose their individuality. The enzyme effector complex loses its individuality. Now it is a different entity. It behaves in a different manner compared to the individual allosteric effector or the individual enzyme. Okay, now effector binding can either increase or decrease the catalytic efficiency. Effector binding can cause the enzyme effector complex to translocate to a different location in the cell. Effector binding can trigger the enzyme to associate with other proteins. Effector binding can also help it can also trigger the enzyme to go and bind with other effectors also at another site. So these are the ways in which the allosteric effectors will uh, affect the enzyme. Okay, so types of allosteric effectors, they can be either be feedback effectors, that is, at the end of the pathway, whatever products or maybe the intermediates are formed, they will bind or associate with one or more enzymes and activate it. Okay, like in a typical reaction where what happens is, like suppose thyroid synthesis, what happens is, so thyroid hormones are getting produced. Okay, in the thyroid hormones are getting produced. They are activated by TSH. TSH is getting activated by, in the pituitary, it is getting activated by the TRH or thyrotropin releasing hormone from hypothalamus. Now this T3 is going to feed back, it is going to give a feedback signal to this TRH. Whenever it is in excess, it is going to cause a feedback inhibition, and whenever it is in deficiency, it is going to cause a activation of TRH. So this is a feedback effector. Similarly, so this is an hormone feedback mechanism, but I have given an example here. Feedback effectors similarly affect enzymes. Indicator metabolites. So metabolic end products or intermediates with a secondary role as allosteric effectors. Okay. So beyond their point of origin, now they may be originating in one particular pathway, but they will go, so it is an intrinsic property, they will go and they will affect another pathway also. Suppose the citrate, which we had discussed in the TCA cycle, this citrate will act as an allosteric activator of beta oxidation of fatty acid. Okay, acetyl-CoA carboxylase is required in the beta oxidation of fatty acid. So this citrate, which is getting generated in TCA cycle, is then going to act as the allosteric effector of acetyl-CoA carboxylase in the fatty acid reaction. Okay, the pyruvate kinase is an enzyme in glycolysis, whereas alanine is nowhere related to glycolysis, but it is going to come and cause allosteric inhibition of pyruvate kinase. So indicator metabolites are across the pathways. Now there are second messengers, very important. They are specialized ligands whose production or release is triggered by external first messengers like hormone or nerve impulse. Now cyclic AMP is triggered by ATP by the enzyme adenyl cyclase. Okay, calcium, it is released in the muscles as a result of excitation by the nerve impulse. Cyclic GMP, nitric oxide, all these are what? Second messengers. Extremely important, and we are going to read about them in detail later on. Okay, so these are the three types of allosteric effectors. Next was, how do you change the intrinsic activity of an enzyme? By covalent modification. Covalent modification again can be either reversible or irreversible. Okay, reversible covalent modification is where when you add certain groups like acetylation, methylation, ADP ribosylation of histone proteins, this is an important example, right? Or post-translational modification. Okay, so what are these covalent modifications? They increase the susceptibility of the enzymes for action. Here, the histone proteins will become more accessible for transcription by acetylation, methylation, ADP ribosylation. You remember how there is capping and tailing of the mRNA? That capping and tailing is a reversible covalent modification of the mRNA. Okay, now what is irreversible covalent modification? Where whatever the changes are getting done, they are irreversible. It cannot go back. That is, one or more proteins or one or more parts of the protein are getting lysed, or it is getting changed. Partial proteolysis. Very important are two pathways inside the body: the digestive pathway and the clotting cascade. In the digestive pathway, we are going to read about these later on in detail. Digestive pathway, the inactive enzymes are going to get converted to the active enzymes, zymogens to active digestive enzymes, or proenzymes to enzymes. Similarly, in the clotting cascade, profibrinogen to fibrinogen. Understood? So this was all for enzyme kinetics and the activity of the and mechanism of action of enzymes and regulation of activity of the enzymes. I hope everything is clear to you. Hill reaction, Michaelis-Menten reaction, the graphs, how different rates of reactions are affected by different factors, enzyme, what enzyme does. Okay, everything is extremely important, whatever we have read. I hope you go back and revise both these sessions. And then we are going to meet in the next session on respiratory chain. Okay, then, till then, goodbye, take care, take rest, bye bye.